Okay, moment of inertia. So, to start with, let's consider a scenario in which we have a race between a solid cylinder and a hollow cylinder of equal radius. So the question is, which one's going to win the race? Now you might think, well, the one with the heavier mass maybe, but as it'll turn out, mass does not have an effect on the outcome of the race. So we're going to figure out who would win the race by considering a concept called moment of inertia. But first, let's just recall from the last lesson that we have these analogs between linear motion, delta x, or displacement, v, or velocity, and a, or acceleration, and their angular counterparts. Delta theta, the angle through which you rotate. Omega, that's the rotational velocity, that's the change in the angle per change in time. And the angular acceleration, which is the rate of change of the angular velocity. They are related to one another through these formulas that I've written in the middle. So the common thread, and this is the one to remember, right, is that the arc length, right, is equal to the radius times the angle. And if you'll recall, this is related to the formula for the circumference of a circle. So if I have a circle of radius r and I rotate around 2 pi radians, which is the same as 360 degrees, then the circumference is 2 pi times r. Related to this is if we do not rotate all the way around, we replace 2 pi with some smaller amount of rotation, call it theta, and now we get that the arc length, the distance around this little arc, is equal to the number of radians that we've rotated times r. And so that is where these transition equations in the middle come from. The acceleration, however, has a couple of components, as does the velocity, I should point out. Because as it turns out, if I consider some little element of mass, and let's say that it has a velocity like this, right? There's going to be the radial component. So this is the distance, not of the big circle that I've drawn, which I should have drawn, I guess, but any velocity in the radial direction, right, will not contribute to the rotational motion. Only that component which is tangential, or perpendicular to this r vector. So we could call this v sub t, and this v sub r. These are the components in the radial and the tangential direction. Only the tangential velocity contributes to rotational motion. So I should really write this as vt. The acceleration, however, has two components. One is the acceleration that is in the tangential direction. So this might be as if the mass was accelerating. If we had like a rocket on a string, right, it would be accelerating because of the thrust of the rocket, but it would also be going in circular motion. The component of the acceleration which is always changing the direction is in the radial direction, and we call that the centripetal acceleration. And it's proportional to v squared over r, or in terms of angular components, r omega squared. Let me just point out that we can develop kinematic equations that are completely analogous to the kinematic equations we had for linear velocities, or linear motion rather. So for example, if we have a constant acceleration, this is the example that we did when we did kinematics early on. And the reason we used a constant acceleration is because at the surface of the Earth, the acceleration due to gravity is approximately a constant. Similarly, we can have the situation where we have constant angular acceleration, and we would write it like this. Next is the velocity, and you'll recall that the linear velocity is equal to the initial velocity plus the acceleration times time, where I'm assuming the acceleration is constant throughout. Analogous to that would be the angular velocity, which can be written as the initial angular velocity plus the angular acceleration times time. Then, of course, we have the x position. You could also call this the displacement, but usually we write it as x is equal to x naught, our initial position, plus the initial velocity times time, plus 1/2 a naught t squared, where this last factor is a consequence of the acceleration being a constant. The analogous kinematic equation for angular components would be theta equals theta naught plus omega naught times t, that's the initial angular velocity, plus 1/2 alpha naught times t squared. And so you can solve a whole host of kinematic problems for angular motion in the same way that you did for linear motion. But that's not all that is analogous. And in the next lesson, we'll talk about other analogous components, like what is analogous to force and momentum. But in this lesson, we're going to talk about what is analogous to mass. So if I consider some little mass component, m sub I, and I'm only going to consider its, well, actually no, I don't want to do that. You'll have some general velocity vector, which will have a radial component. So I'm going to put a point of rotation here. I'm going to draw a line to that little mass and call that the vector r. This velocity component can be broken up into its radial components, v sub r, and its tangential components, v sub t. This is what we talked about earlier. So as I said, the v sub r does not affect the radial motion at all, or rotational motion at all. And what I want to do now is I want to write the kinetic energy for a system of little masses like this. We might have a whole bunch of them scattered throughout. You can think of them as little particles if you want. They may or may not be attached to each other in some way. Could be a rigid body, like a large disk, or say a cylinder.
Right.
Or they might be disconnected, like a gas. Okay?
Oh.
So how do we write down the formula for the kinetic energy for this guy? Well, the kinetic energy, T, is going to be equal to 1/2 the mass sub I, this little particle here, times v sub r squared. This will be the component that contributes to the motion of the center of mass. Because remember, there's a whole bunch of them, right? And this is the component that will contribute to the center of mass motion.
All right.
That is, if the whole object is moving, right? It will be a linear motion. But we also have a rotational component, and these should have subscript i's on them, I guess. V sub I, r, for the radial component of the ith particle. And then here we have 1/2, and this should be T sub I, I suppose. Mass sub I times V sub I tangential component squared. This is just the usual formula for kinetic energy, but I've broken up the radial and the tangential components of the velocity, okay?
Okay.
There's not much to do with the radial component, but the tangential component, 1/2 mass, we can use the formula up here that V sub t is equal to r omega. And so this will become r sub I omega sub I quantity squared, using this relationship right here. If we want to get the total kinetic energy for the entire system of particles, then all we have to do is add up all these little kinetic energy components of all these little masses. Right? So we add up all the particles. And if we do that, we'll get the sum over 1/2 m sub I v sub I r squared plus the sum over I of 1/2 m sub I r sub I squared omega sub I squared. And we can write this as 1/2 big M times v cm squared, where this is the center of mass of the system of particles. The big M is the sum of all the individual masses, okay?
Okay.
Plus 1/2 I omega squared, where I is given by the sum of all the masses times r squared. Right? So each particle will have a different r, right?
Yeah.
So this is in general a kind of a complicated thing to calculate, and this we call the moment of inertia. And if you compare the two pieces, right, we've got a 1/2 mass times velocity squared, and here we have a 1/2 something times angular velocity squared. So you see why I say the moment of inertia is analogous to the mass, right?
Yeah.
Because it sits in the same spot where the mass does in the linear component, and the linear motion component of this, right?
Yeah.
Like I said, this is not the easiest thing in the world to calculate. If you only have a few particles, it's not hard, right? Because you're just going to sum over a few components, right? The mass of one thing times the distance from this this rotational center, right? This is the point at which they're rotating around, okay?
Okay.
So there's some rotation that's going around like this, right? And then the center of mass motion, right? The whole thing might be going in some direction like this. So you've got some velocity at the center of mass. The whole system of particles is moving, but it's also rotating. So it's like if you took a bicycle wheel and get through it, right? So it's rotating, right? But it's also traveling. You remember that the complex motion of rigid bodies, right, can be simplified by considering just a point called the center of mass, which we talked about in a couple of lessons ago, I think. And in that case, it follows a very simple trajectory, just as it would if it was a single particle. Okay?
Okay.
So typically you use calculus to solve these. Let's determine the moment of inertia for various things. I'm going to give you a couple of simple formulas that apply to the cylinders that I talked about at the beginning. One is a solid cylinder, as we call it a disk, right?
Okay.
And that is something whose shape, something like this in 3D, where all the axis of rotation coming out like this, right? And here, the moment of inertia is equal to the mass, the total mass, times r squared, where r is the radius of the cylinder. That's not as clear as it could be. R is the radius of the cylinder. Okay?
All right.
And for a hollow cylinder, technically with infinitely thin walls, by the way, the moment of inertia for this is 1/2 mr squared. I think I got these backwards. Yeah, my bad. I thought it looked wrong. The solid cylinder is 1/2 mr squared, and the hollow cylinder is just mr squared. Okay?
All right.
So why should one be greater and the other be smaller? Well, have you ever seen an ice skater skating on an ice rink, and they do those tricks where they hold their arms out and they're spinning around, and then they bring their arms in and they start spinning much, much faster?
Yeah.
That's because they've reduced their moment of inertia. Okay, they have the same amount of energy, but they've reduced their moment of inertia, and what happens is they speed up, right? Because if you have an object, right, which has a large moment of inertia, that means it's hard to rotate. In the same way that an object that has a lot of inertia, i.e. a heavy mass, is hard to get moving, right?
Yeah.
So it's easy to push, a toy car, but it's hard to push a real car, because the real car has much more inertia or resistance to motion than the toy car does. Okay?
All right.
And so we get the same thing with a moment of inertia. Things with a large moment of inertia are hard to rotate. They resist rotational motion. Okay? So as you can see, solid cylinder has less moment of inertia than the hollow cylinder does. That's because all the mass, let's say the mass could be the same in these two, but all the mass is distributed out on the circumference, out at the outer edge of it, right?
Yeah.
So if you can imagine holding a stick that weighs it weighs 10 kilograms, right? But that mass is equally distributed throughout the stick. You try to rotate it. Now you imagine the same stick, but all the mass is at the ends of the stick, right? That's going to be harder to rotate. Because again, the formula for inertia is the sum of all the particles, their masses, times the distance from the rotational center squared. Okay?
All right.
And that r squared term, because it's squared, it plays a big role. So you can increase the mass of something, and its inertia, its rotational inertia, or moment of inertia, will go up linearly with mass. But it goes up like the square with the radial distance away from it. Okay?
Okay.
So now I want to think about one of these cylinders and rolling motion. Okay? And so what is rolling motion? Well, it's a combination of two things. Right? So let's imagine we have a cylinder. Okay? And we have, let's let it slide. We're just going to let the whole thing slide. There's no rotation at all involved. And this we'll call the center of mass. Okay? The center of mass will be going with some velocity v as it slides, as will a little, a piece of mass on the bottom of the cylinder will also be going with the same velocity v, right?
Yeah.
As well, a piece of mass on the upper part of the cylinder, right? Every part of the cylinder, the whole thing is going in this direction with some velocity v. And we'll call this sliding. And if we combine sliding motion with rotational motion, this time, this is purely rotational. So the center of mass, if I draw this, v here is equal to 0. It's not moving in this direction. The only thing it's doing is it's rotating. We'll give it a rotational velocity. The top will be going with velocity v in this direction, but the bottom will be going in the opposite direction. Right? We'll call it minus v. Okay?
All right.
So you can see it's just spinning around like this, but not translating in the linear direction, right?
Yeah.
If I put these two together, right, using vector addition, right, what does the resultant motion look like? Well, the center of mass, we have v plus 0 is v. So the center of mass motion will still move with v. Okay?
Okay.
What about up here at the top? Well, here we have v plus v, that's 2v, right? So the top will be moving with a velocity which is 2v, twice that of the center of mass.
All right.
What about the bottom? Well, here we have v plus negative v. What's that equal to?
0.
That's equal to 0. So the motion at the bottom is 0. And so think about this when you see a car tire rolling on the ground. Imagine it moving slowly. At the point where the tire touches the asphalt, right?
Yeah.
The velocity of that little piece of the tire is 0. It's not moving. It's stationary.
All right.
Now, if you were to hit the gas really fast, it might slide and leave a track, right? You see those black streaks that you sometimes see on the road?
Yeah.
That's sliding. That's sliding motion. That's this. That's what happens when the velocity of the bottom of the tire that touches the road has some motion, linear motion to it, right?
Yeah.
It just results in rubbing the rubber off of the tire and depositing it on the road. But when they're just driving,
Oh.
we have rolling motion, okay? So rolling motion is sliding motion plus rotational motion. Call this rolling motion. And so this is what happens in our race when we roll these two cylinders down a ramp, okay?
Okay.
Let's consider the race. I'm actually going to draw it a little bit differently than we have it set up, okay?
All right.
Just so we can see the two pieces. What I'm going to do is I'm going to imagine a ramp, two ramps actually, that both make the same angle theta, right, to the ground. So this angle and this angle are the same, all right?
All right.
And the height on both sides is the same. Put the hollow one on this side, I'm going to put the solid one on this side. And we want to figure out who wins the race, okay?
All right.
If this angle is the same and this height is the same, that means that this length, this track they're going to travel on is the same. And so we want to know, if we want to know who wins the race, we need to know which one goes faster, okay?
Yeah.
And we're going to use conservation of energy to figure that out. So you might recall that conservation of energy tells us that the kinetic energy, the change in the kinetic energy has to be equal to the change in the potential energy. And what is the potential energy over here? And we're going to also, let's assume they're both of mass m. Turns out not to be important, but let's just assume that for now.
All right.
The potential energy, right, is mgh, right?
Yes.
You might remember that from when we talked about gravitational potential energy, right? So if I want to figure out how fast something is going if I drop it, if I know the mass of this pen, and I know how high it is above the floor, I can easily calculate how fast it's going to be right before it hits the ground by setting its kinetic energy 1/2 mv squared equal to mgh. Solve for v, and I have its velocity, okay?
Okay.
We're going to do the same thing with the ramp. Let's consider the solid sphere. mgh will be equal to 1/2 mass times v. I'm going to put v sub s for v solid, okay? This is its center of mass velocity, by the way, right? Plus 1/2 I sub s for the solid, moment of inertia, times omega sub s squared. Does that make sense? That's what we talked about here at the beginning with kinetic energy. We have the two components. So the linear component, that's the center of mass motion, and the rotational component, okay?
Okay.
And when you put energy into something like we're doing here, we're putting energy into it via gravitational potential energy, just as I'm putting energy into this pen via gravitational potential energy, right? But all of the energy is not going to go into the center of mass motion. Some of it has to go into the rotational motion, okay? Though it's implied, I'm not saying it specifically, that it's going to undergo rolling motion, okay? And that's what will happen if you have some friction involved, okay?
All
We don't need to talk about the friction or even include it in our equations, but all we need to do is assume that it's rolling motion. If we assume that it's rolling motion, it means that we assume that it has a linear component and a rotational component to the energy. So I can substitute in, right, because what is IS? Well, IS, we already have that over here. I guess I should write it like this. IS and IH for hollow. IS is 1/2 mr squared, right? What about omega s? Well, omega s I can get from this, right? It's just equal to V over R. So I can rewrite this. All right, so we can factor out a 1/2 mass times V squared from both of these two terms. This is equal to 1/2 mass times V sub s squared times 1 plus 1/2 is all that's left behind. That's the same thing as 3/2 times 1/2 mass V sub s squared. Now, there's a reason I'm keeping the 1/2 mass V sub s squared around, and you'll see momentarily. But notice also that I can cancel out mass from both sides. I told you at the beginning that the mass won't make a difference. They can be different masses, it won't affect the outcome. Okay, because this mass, remember this is mgh over here, this mass will cancel this mass. And so I'm left with just gh equals 3/2 times 1/2 V sub s squared. Okay?
All right.
For the hollow cylinder, everything is pretty much the same, right? We'll start out with mgh equals 1/2 mv sub h squared plus 1/2 I sub h omega sub h squared. Except we'll substitute in I sub h will be what we get for the hollow cylinder for the moment of inertia, right?
Yeah.
And I'm going to skip the algebra on this one because you can kind of see what we get. Instead of having 1 plus a half, we'll have 1 plus 1, right?
Yeah.
And so that's going to give us that GH is equal to 2 times 1/2 V sub h squared. Okay? Actually, I'll call this star sub s and star sub h. Okay, so if I simply divide star sub s by star sub h, we now get GH over GH is 1, and that's equal to 3/2 divided by 2. We'll make this 3/4, right? V sub, and then the 1/2 factor will cancel in both of them, right? And I'll have V sub s squared over V sub h squared, which means that I can solve for V sub h squared. V sub h squared is equal to 3/4 of V sub s squared. So which one is faster?
V sub S.
Yeah, V sub s, because V sub h is only 3/4. Really, it's the square root of 3 over 2, the velocity of V sub s, right?
Yeah.
So this says that V sub s is greater than V sub h. And so who's going to win the race? Right? V sub h or V sub s? Well, if V sub s is greater than V sub h, then this guy will win the race because he'll get to the bottom quicker because he's going faster. I know it's a little anticlimactic, right? But we can, look at the experiment and we'll see that this is in fact true. Okay, the solid cylinder will win because its moment of inertia is smaller. Okay, so less energy will be put into the rotational motion. Okay, because it doesn't resist rotational motion as easily. Okay, is that what you expected? Is that the result you expected? Did you expect the solid? Now, in our case, right, the solid was actually a little bit heavier because it had filler in the center of it, right?
Solid.
The radiuses were the same, though. Okay, and that was more important than the
Weight.
weight. Yeah, so that is the result. Okay, and it's because of the smaller moment of inertia of the solid cylinder. That's all I'm going to say about that. We'll have one more lecture or lesson on angular motion, and we'll talk about the analogs, the angular analogs to force and momentum. Okay?
Okay.
It won't have a whole lot to say, but we'll talk about it a little bit and work out a very simple example. And I think also we'll see for the first time friction.
Okay.
Because this is one place where I can put it in, and it's something that's tractable at this level of mathematics. So that's it for now.